Why can birds sit on power lines all day long, but we fry if we touch a live wire? Let's start with these. Batteries. Most of these batteries have 1.5 volts of electric potential when brand new. That's potential to do something useful like provide light. Let's connect this D battery to an LED. Doesn't work. You know why it's not lighting up? Because light-emitting diodes need more than 1.5 volts, as do most electronic devices. That's why you need to use at least 2 batteries for most devices. The batteries are connected one after the other in series. Now, we try again with our LED, and this time, it works. Do you know why we call it volts? Science likes to credit the inventor with a new discovery's unit of measure. So volts and voltage are named after Alessandro Volta, Italian physicist who invented the first electric battery in 1800. This one produces 9 volts and can power a wide range of devices like smoke detectors. What happens if we connect this 9-volt battery directly to our LED? Let's try it. We just blew it up because it can't handle that high a voltage. We'll explain how we solve this problem in the next video when we talk about electric current. There are bigger batteries like this one in garage door openers, useful when there's a power failure, and car batteries. Both have a voltage of 12 volts. So where does this voltage come from? A battery works through an electrochemical reaction. You need 2 different metals like copper, zinc, and some acid like lemon juice. The metals have different electrode potentials, and the acid allows electrons to move between them, creating a voltage. These 3 items make up a cell. Will this power an LED? Nope, not enough voltage. We need to add more lemons. Here's 2. Still nothing. How about 3? Yes, but not very bright. Let's try 4. Much better. There's another way to generate voltage. But first, if you're enjoying this video, give it a like and turn on notifications so you don't miss the next video with the next most important electrical idea, current. Thanks to physicist Michael Faraday, we can create electricity without lemons. He discovered that a changing magnetic field creates a voltage in a nearby conductor. We can see this in action by passing a magnet through a coil and observing on the voltmeter. Notice that when I change the direction of motion, the voltage reverses. When I pull out the magnet, the needle moves to the right. But if I swap the wires to the meter, now the needle moves to the right when I push in the magnet. If instead of moving a magnet in and out of a coil, you spin a coil in a magnetic field, you've created a generator. And it can generate power when connected to a wind or water turbine. So far, we've been talking about DC voltages plus and minus. On an oscilloscope, which shows how voltage changes over time from left to right, a DC voltage stays fixed. It's just a horizontal line. But there's another kind of voltage, AC. Power in your house is AC voltage. Instead of a constant voltage, AC voltage changes over time. It goes up and down like this. Voltage goes up and down 60 times every second. That's why it's called 60 cycles per second, or 60 Hertz, named after Heinrich Hertz, German physicist who proved the existence of electromagnetic waves, shaped like this, a sine wave. The peak voltage of the sine wave in the power grid for the US and Canada is 170 volts. So why do we call it 120 volts? If you determine the effective voltage delivered by flipping the negative portions of the sine wave, then averaging, you get 120 volts, called the RMS voltage. AC voltages do not have plus and minus connections like batteries. Instead, 120 VAC has a live or hot connection and a neutral connection. The wider slot is the neutral. This matches up with some plugs like this, so you can't plug it in wrong. But what is this other connector in the receptacle? It's a connection literally to ground. It's used every time you plug in something that has this third ground prong. Why is it here? Safety. It provides an alternative path for the electricity. For example, if you're using a leaf blower with an extension cord that does not have a ground, and you happen to touch a damaged part of the cable, the electricity will go through your body to ground. Ouch! But if you use a grounded extension cord with the third prong, the electricity now has an alternative path through the ground wire in the extension cord, then safely to Earth. Nobody gets zapped. This is a clue to the bird question we will answer later. Where does this voltage come from? All of the power in your house connects to the circuit breaker box, usually outside. Here's a peek at all the connections to the circuit breakers. And this is connected underground or in overhead wires to the power grid. Somewhere on your street, you'll find a residential transformer that converts the incoming voltage from 7200 volts to 120 volts that goes to your house. A quick aside about transformers. You've seen these plugged in all over your house. Power supplies for all your gadgets. Let's open one up. Most of these have a small transformer to convert the 120 volts to lower voltages needed by your devices. Here it is. It has two coils wrapped around an iron core. The input AC voltage creates a magnetic field that induces an AC voltage on the output, and the ratio of coil windings determines the output voltage. For example, if the input coil has 1,000 loops and the output coil has 100 loops, output voltage will be 1/10 the input, or 12 volts. So the residential transformer with 7200 volts input and 120 output has a transformer with a turns ratio of 60:1. If you follow the wires from here, you'll end up at a substation. The substation has a much larger transformer that reduces the voltage from an incoming 69,000 volts or 69 kV to 7200 volts. And if the power source is far away, there's an even greater line voltage of up to 500 kV across tall transmission towers. Why does the voltage get increased so much? Because there's much less wasted energy in the form of heat at these higher voltages. That means cheaper power. Severe weather is the leading cause of high-power line failures. This includes damage from wind, heavy rains, and ice storms. Just like your house wiring, the substations are grounded for safety of the equipment. When a fault occurs, a current to ground is detected quickly, enabling a protection circuit to cut power to the equipment before it gets destroyed. Grounding also protects the grid from lightning strikes. Those towers are very tall. By the way, lightning bolts generate millions of volts of potential. The wires from here go to the power generating station that produces 30 kilovolts, so we need another transformer to match voltages. The generating station can be a coal plant, nuclear generator, hydro dam, wind farm, or solar array. Now let's get back to the question. Why birds don't get electrocuted when they perch on high voltage wires? Did you figure it out? The key idea is that voltage is electric potential difference. It's measured between 2 points, just like we did using our voltmeter and the batteries earlier. Until we connect both leads, there is no voltage displayed. When we connect across the two batteries, the meter shows 3 volts, 1.5 for each battery. If we place both leads on the same battery connector, there is no potential difference, so the meter shows 0 volts. This is similar to the crow's position with both feet on the same wire. Same potential, no net voltage. He's safe. But for a down wire, it's a different story. Remember that the whole power grid is grounded to protect the equipment. Ground is 0 volts. Our victim's hand is at 7200 volts, but his feet are at 0 volts. So 7200 volts are going through his body. He's a goner. Never touch down power lines. But do click this next video. It's electrifying in a good way.